Okay, so let's say that S is a surface with a given parameterization, and let's say that it has a given mass density. Then we want to find the mass of the surface. So I'm just going to go back up to this picture here. Okay, so basically here we assume that it had a uniform mass density. Now we're going to assume that it doesn't have a uniform mass density. So now the area is what we get. The surface area is given by or represented by this Riemann sum here. How do we make this work for mass? Okay, so just keep that in mind. I'm going to come down here. And now the mass is going to be roughly the sum k equals 1 to 5. I think k went from 1 to 5. And j goes from 1 to 4. J equals 1 to 4 times delta evaluated at sk tj times delta a kj, and this is roughly equal to the sum k equals 1 to 5, j equals 1 to 4, delta of sk tj times rs evaluated at sk tj cross rt evaluated at sk tj delta s delta t. Now I'm running into writing from the previous problem. Okay, so what we're saying then is that the mass of each one of these patches is equal to the mass density evaluated at one point in the patch times the area of the patch. This is very similar to how we've done integrals throughout all of your calculus life. It's the area of the base times the height, or the area of the base times the mass density, or the area of the base times whatever it is that we're integrating. Okay, so this is the Riemann sum. So what does this mean? The mass then is going to be equal to an integral. So the mass is equal to the integral over the parameter domain d delta of st rs of st, or the magnitude of rs evaluated at st, times rt evaluated at st ds dt. And in general, if S is a surface with a given parameterization and f is a function defined on R3, then the surface integral of f over S is the following. So here f is a function, the ds is the surface measure, so this is going to be the integral over the parameter domain D, f of x of st, y of st, z of st. Okay, now let me erase this part from the previous problem. Times rs, the magnitude of rs cross rt, ds dt. But really, instead of writing ds dt, what we should be writing here is dA in the st plane. The dA is the dA in the st plane, and we're integrating over the parameter domain D. Okay, so this surface integral, we compute this. So the surface integral is defined as its own thing. One way that we can compute it, if we have a parameterization, is this formula right here. And essentially, this is the only practical way to compute a surface integral of a function like this. Okay, in the next couple of videos, we're going to look at examples. In the previous examples, we are computing surface integrals where f is just the constant function 1.